Homework M1, question 4. We've got a rare species of primrose being modelled by this equation here, p equals 800 e to the 0.1t over 1 plus 3 e to the 0.1t. And in part A, we're asked to calculate the number of primroses at the start of the study. Start of the study is when t is equal to 0. At t equals 0, p is equal to 800 times e to the power of 0 over 1 plus 3 e to the power of 0. E to the power of 0 is 1, so that's 800 over 1 plus 3. 800 over 4 is 200 primroses. In part B, we're asked to find the exact value of t when p is equal to 250, and we're given a format that we need to work with, that is a natural log b, where a and b are integers for us to find. So I sub in p is equal to 250. 250 is equal to 800 e to the 0.1t all over 1 plus 3 e to the 0.1t. If I times up by my denominator to get rid of my fraction, 250 plus 750 e to the 0.1t is equal to 800 e to the 0.1t. Rearrange. 250 is equal to 50 e to the 0.1t. E to the 0.1t therefore is equal to 5. And this is where I take natural logs of both sides. So log 5 is equal to 0.1t, and times up by 10 to eliminate the 0.1. 10 log 5 is equal to t. In part C, we're asked to find the value of dp dt when t is equal to 10, giving our answer in its simplest form, which is going to mean not rounding it but finishing it in terms of e. So we're going to need to use the quotient rule, where in terms of the letters we got dp dt is equal to v du dt minus u dv dt all over v squared. U is my numerator, v is my denominator, so I need to differentiate each of these. Using the chain rule, du dt is equal to 80 e to the 0.1t, and dv dt is equal to 0.3 e to the 0.1t. Plugging these four values in, I get dp dt is equal to v du dt, so that is 1 lot of 80 e to the 0.1t plus 3 lot e to the 0.1t times 80 e to the 0.1t, so that's 240 e to the 0.2t. And from that I take away u dv dt, and 800 times 0.3 is also 240, and e to the 0.1t times e to the 0.1t is e to the 0.2t all over v squared, 1 plus 3 e to the 0.1t all squared. So this term here and this term here are going to cancel out. But rather than simplify at this stage, I'm also going to plug in the at t equals 10. So dp dt is equal to 800 e to the 0.1t, where t is 10, so that's 0.1 times 10 is 1, 80 e all over 1 plus 3e squared. And that's it in its simplest form. In part D, I'm asked to look at the long-term behaviour of the question to explain why the population of primroses can never be 270. I've rewritten my original equation by dividing the numerator and the denominator by e to the 0.1t. That just gives me 800 on the top, and 3 plus e to the minus 0.1t on the bottom. Long-term behaviour is as t tends towards infinity. And as t tends towards infinity, e to the minus 0.1t is going to tend towards 0. Therefore p is tending towards 800 over 3, which is 266 and 2/3. So this is my limit that I'm going to be heading towards. Now I need to know what side of that limit I was actually on, and in part A we said that we were starting with 200 primroses. So we're only ever going to get as high as 266 primroses. That's all I need to write as the maximum number of primroses is 266, we can never reach 270.